Hello everyone. Today we are going to learn about one of the important processor in digital electronics, that is Intel 8085 microprocessor. Although modern computers uses microprocessor like Intel Core i7 or ARM processors, almost every processor is built on concepts introduced by 8085. Therefore, understanding the basic 8085 microprocessor helps us to understand the modern computer architecture. At the end of this lecture, we'll be able to understand to define a microprocessor, explain the feature of 8085 microprocessor and also its architecture, identify the registers, use of registers, and how data moves inside the microprocessor. So now, what is a microprocessor? The microprocessor is nothing but what happens when you press a calculator button. In 5 plus, when you press the button in the calculator 5 plus 3, it gives the answer 8. So now, in order to explain the function of a calculator is nothing but what's happening inside the calculator is the actual process of a microprocessor, what is exhibiting to perform the operation of 5 plus 3. Okay, so that is the process of a microprocessor. So now here microprocessor will call the brain of a computer because it receives a data, processes a data and stores the temporary results and sends the output. So sends the output in the sense in order to store it in the memory. Okay, so now the Intel 8085 was introduced in 1976 and it became one of the most successful 8-bit microprocessor. Okay, so now coming to the feature of 8085 microprocessor, it is a 8-bit microprocessor, which means it accesses 8-bit at a time. Okay, and in order to process a 8-bit at a time, so it needs a data bus and also where the data is located, it needs the address bus. So so it adds a features of an 8085 microprocessor is 16-bit address bus in order to find a location of a data. Okay, and the other feature is 8-bit data bus. So in order to carry a data, okay, which means 8-bit data, and its maximum memory size is 64 kilobyte memory addressing, and the power needed to process all these operations is single 5 volt supply. Okay, and it has a 40 pin IC, and also its operating frequency is 3 to 6 megahertz. Okay, and why why it is called as a 8-bit microprocessor is nothing but, as I already told you, that it can process 8 bits of data at a time. So 8 bits. So now coming into your mind as a question like, so what is 8 bit? So 8 bit is nothing but a zeros and ones combination of 8 digits. Okay, so example, I can tell you that if it is a 8 bit, 11001010 is nothing but an example of 8 bit. So these many bit can be accessed by the 8085 microprocessor at a time. So concluding or summarizing it, we'll be calling it this 8 bit as 1 byte. Okay, so now, so as a day-to-day life example, comparing it with the 8085 microprocessor is, imagine that a post office. Okay, so what will happen in the post office? The function of post office will receive a letter from different addresses. Similarly, here the address bus also tells where your data is located, and the data bus carries what data should be transferred to the particular location. So think of it interpreting this to address bus, where the address bus indicates the house number, where the data represents the parcel, and here the control signal represents the traffic police deciding whether to read or write a signal from the memory and to the memory. Okay, so this is how you have to understand how the microprocessor is operated. Okay, and next is your pin diagram of the, as I told you that it is a 40 pin IC. Okay, so there are the 40 pins which is accommodated by the, as I have explained already in the features of the 8085 microprocessor. There are several control signals is exhibited by the 8085 microprocessor, and also address bus, 16-bit address bus, so that you have A0 to A15 is your address bus, and data bus is AD0 to AD7. Okay, so these are the address bus. So with all this has been built by the pin diagram of the 8-bit microprocessor. Then coming to the architecture, I mean the internal blocks which is used to form an 8085 microprocessor is nothing but the architecture of your microprocessor. So in the architecture of your microprocessor, we have three main units, which is nothing but arithmetic and logical unit, timing and control unit, and array of a register to hold the data when it is being processed. Okay, according to the user defined function. Okay, so with this basic unit only, your entire process can be completed or furnished according to the user defined function. Okay, so here coming to the arithmetic and logical unit, it will help us to perform addition operation, subtraction operation, division operation, multiplication, or logical operations, and or all these operations can be done. So to exhibit this ALE operations, okay, the several control units to be activated. So only then the process can happen by the ALE unit. So for that, the timing and control signal is necessary. And then, so once the timing and control signal is being activated, your data to be taken by the particular memory through the register. So for that, we need to have a register operation. So now we'll see one by one block of explanation. Okay, so what all the blocks we have here is, as we have known, the main block is nothing but the AL unit, which is nothing but the arithmetic and logical unit. So arithmetic and logical unit performs addition, subtraction, and or XOR and comparison operation. So for example, if I want to have 25 plus 15, and if I want to add 25 plus 15, so that can be computed, this calculation can be computed by the ALU unit. Okay, this part will be able to compute this addition operation. And where does the result will be stored? In the sense, it is stored back to the temporary register through the accumulator, and that will be stored into the external memory location. And next up, we have the register array. Okay, so register array is nothing but the very small storage location which is built in the CPU section. Okay, so what are all the that registers which are available in 8085 microprocessor? In the sense, there is a general purpose register which are like B, C, D, E, H, L. These are the general purpose register we have in a 8085 microprocessor. Individual registers are an 8-bit register. So combining these registers, we call it as a registers pair, and this register pair holds a 16-bit data. So BC register pair, DE register pair, HL register pair. We have three register pair which can be used to hold a 16-bit data. This W and Z are called the temporary register, and these are the special function registers: stack pointer, program counter, and accumulator, or the temporary register. Okay, so and then now we have a special function register which is nothing but the program counter. So the function of the program counter will store the address of the next instruction. So how does the processor will come to know which instruction to be next? Is nothing but by the program counter values which is stored inside the program counter only. The processor will come to know this is the next instruction which microprocessor want to execute. Okay, so that value will be stored in the program counter. So the next stack pointer works like it's a stack of books. The last book placed on the top is the first one to be removed. So this concept of this concept will be used by the last in first out. Whatever the last recent data which is stored inside the memory will be taken out first. Taken out first in the sense removed first. Will be accessed first. Okay, and next one important structure of register special function register is nothing but flag register. So flag register is we have so the importance of flag register is nothing but whatever the result after every operation or after every execution of the ALU unit, the processor will check the result, and those result will be the status of the result will be updated in the flag register. Okay, so there are the 5 flags, which is nothing but sign flag, zero flag, auxiliary carry flag, parity flag, carry flag. Okay, so these are the flags which are available here: sign flag, zero flag, auxiliary carry flag, parity flag, carry flag. So the function of sign flag will indicate the sign of the accumulator. So whatever the computed result or the processed result, whether it is a positive or negative, that will be indicated by the sign flag. So for example, if the result process result is negative, means in this particular bit it will be showing as a 1. Okay, and if it is positive, means it will be showing as a 0. Okay, so that is nothing but the reflection of the sign of the processed data. And next is zero flag is nothing but like when you process the result, if your resultant is zero value. Okay, so in that case the D6 bit will be 1. Okay, and this is your don't care condition. It can be anything, either 0 or 1. And auxiliary carry flag is nothing but, so when you perform your addition operation, in that case, if you have uh, if you have carry bit from D3 to D4. Okay, when you have excess bit, when you perform an addition operation from D3 to D4, means in that case your auxiliary carry flag will be 1. Apart from this, your auxiliary carry flag will be in reset condition. And next, parity flag. So parity flag is nothing but, so if there is even number of ones in your result, means then your parity flag will be set. Otherwise your parity flag will be 0. Okay, so carry flag is nothing but when uh, whenever you perform an addition operation, your D7 bits overflow, means in that case your carry flag will be set to 1. Okay, in case of arithmetic operation. Similarly, in case of a subtraction operation, when you have a borrow exist beyond this on bit, means in that case your carry flag will be 1. Otherwise your carry flag will be resetted condition, which means 0 condition. Okay, so this is what the I mean process of an flag register. So whatever, so concept of flag register is nothing but whatever the result is processed by the processing unit, which is nothing but the arithmetic and logical unit, means so those reflection of or status of the result obtained by the microprocessor will be stored back into the flag register, which flag register. Okay, and next is timing and control unit. So timing and control unit, we have many I mean uh, control signals, which is nothing but hold, acknowledge, and all that. So when these control signals are being active, in the sense whenever the processor is busy with the current operation, means in that case your the other operation which is which wants to handle by the microprocessor will be put and hold. Okay, so that when it is put into an hold condition or hold state, So it will be sent through an acknowledge signal. That is nothing but the hold acknowledge signal. So these are the, and whenever you want to perform or write into your memory or take the data from the memory, means the set of control signals we have RD bar and WR bar. So when the RD bar will be activated, in the sense whenever you want to take a data from the memory, in such case RD bar will be active. Okay, WR bar, when the WR bar will be active, in the sense whenever you want to store the data into the memory, means in that case your WR bar will be active. So which is actually a read bar example. The better example of a read bar signal is reading a newspaper. Okay, you are retrieving the data to the brain of a computer. That is nothing but the read operation. Write operation is writing a data by the use of pen in a paper is nothing but the write operation. Okay, so this is a best. Likewise, we have a set of control signals which is used in a microprocessor. So as we have already explained, that address bus, data bus and control bus. And one more important thing, how it is being directed. So address bus is a unidirectional, and also it identifies the peripheral or the memory location. Peripheral is nothing but the external device, like connecting an USB device or processing any, external devices. That is nothing but the peripheral devices. And data bus is nothing but the bidirectional device, which helps us to transfer your data from the memory and to the memory. So control bus is also unidirectional. Only processor will have a control over all the accessing units. Okay, so that is what the unidirectional device. So program counter, as I have explained you already, that it is able to, or it stores the address of the next instruction. Okay, so stack pointer is used to store the current memory location, what it actually want to be executed. Next, coming to the instruction set. So in order to process all this type of data, okay, all this set of processing, okay, so how does that microprocessor, since it is a digital device, right, how does the microprocessor will understand a human language? That uh, how does the data is being processed, we need to understand it. Okay, so that that has been fulfilled by the concept of the 8085 instruction set. So now we need to understand what is instruction set. So what is the use of instruction set? So instruction set is nothing but the binary pattern designed inside the microprocessor to perform some specific function. Okay, so and the entire group of instructions that a microprocessor support is called a instruction set. So in a simple language, the instruction is nothing but a command given to the microprocessor to perform a specific operation is nothing but the instruction. For example, to add a number or copy a data or compare a values or jump to the another location or read from an external device, which is nothing but the input device, is all these sort of processing and operation will be coming under the, is like commanding a instructions, is nothing but the instruction set. Okay, so there are the basic 74 basic instructions which can be grouped into a 6 categories. Okay, so one such category is, which is displayed here, is data transfer instruction, arithmetic instruction, logical instruction, branching instruction and control instruction. Okay, so data transfer instruction is nothing but it helps us to move your data from one location to the other. Okay, they do not change the data, but actually what is there is to be copied. It's just copying a data from one location to the other. What we do, copying data, word format or excel data, whatever the document, from one folder to the other. Okay, so that is nothing but the data transfer instruction. So and arithmetic instruction is nothing but, arithmetic and logical is nothing but to perform addition operation, subtraction operation and operation and all that. Branching is nothing but when you have a decision making operation, in such case the branching instruction can be used. Control instruction is nothing but if you want to control a microprocessor directly, for example, turn off it, or you want to interrupt the current processing. In such case, you can make use of this control instruction. So these are the 6 type of instruction we are going to see one by one. Okay, so in case of data transfer instruction, the instruction move your data between the registers or between the memory and the registers. Okay, so which means the instruction copy a data from a source to destination, but the source will not be changed. Only the destination content will be changed while copying that. It is actually resembling the operation of copying a data from one location to the other, meaning that the content of the source are not modified. Okay, so now, so one of the instruction or the mnemonic which we use is that move instruction. Okay, so RD, RS, where RS represents the source and RD represents the destination. Okay, so we have here many general purpose register, which is nothing but B, C, D, E, H and L, A and also. Okay, so in this case, so individually these registers can be used as a 8-bit registers. Okay, when it want to access a 16-bit, you can use it as a pair, which is nothing B, C, D, E and HL pair. Okay, so instruction copies the content of a source register to the destination register. As it already explained, the content of a source register will not alter. Okay, but the destination register will be altered. Okay, and coming to m comma rs is nothing but, so you have this m is nothing but the memory location where your data is to be copied, is nothing but the represented by the m. Okay, and similarly here, so from m represents the memory location where your data is available. Okay, example can be move b comma c. For example, in this case what you have is that, so if you have before execution, before execution in these two register, if you have in C register if you have 35 and B register if you have 25 means, so after execution of this particular instruction, what happens here is C holds a 35 means B holds a 25 as a data means 35 number will be copied into a B register. So now after the execution, the C register have 35 and B register will also have 35. It will be changed from 25 to 35 because we are copying the data from C register to the B register. Okay, and here in this case move B comma M means holding the memory location. So memory will be a 16-bit data. Okay, so from the 16-bit data, for example, let's take a 16-bit data of 4600. In this 16-bit data 4600, we have 35 as a data pointed by the memory location, which is nothing but the M means 35. And if you have B as similar example as 25 means, so after execution of this instruction, B holds the 35 and this memory location also will remains the value of 35. So this is the concept of the move instruction. Okay, so MVI means RD comma data. RD means destination, data is the source. That means immediate data, which is nothing but the 1D 8-bit data. And similarly, when coming to the example, MVIB comma 57 is nothing but the 8-bit data. This data will be loaded into the B register. Okay, so whatever the data which is stored in the B register will be changed to 57. And similarly here also. Okay, so this M is holded by the HL register pair. Okay, so this is what the concept of the MVI instruction. LDA is also to hold the get the data from the memory location to the accumulator. Okay, so that is the concept of load the data from the memory to the accumulator. So this is an example. LDA 2034 means, so from this memory address your 8-bit data will be loaded into the accumulator. Okay, so that is the concept of the LDA instruction. And next LDAXB means the content of a destinated register pair will be pointed by to the memory location. Okay, so now let's come directly to the example. Okay, example we are taking here as a LDAX B. Okay, so now this B here in this case B is nothing but the where B holds the memory location of where your data lies. Okay, so memory location means it holds a 16-bit data. So which means this B is nothing but the 16-bit register pair. 16-bit register pair holds the memory location, okay, where your data lies. So in this BC, so BC, for example, where your data lies is pointing by the address is 4600. Okay, so now BC register holds a 4600, means in this 4600, consider that I have a value, and the processor has a value as 15. It's an 8-bit data that will be moved to the accumulator. Okay, so which is actually the instruction loads the content stored in the memory location which is specified by the register pair BC into the accumulator. So basically this BC register pair hold the memory location where your data lies. Okay, so that particular data will be copied into the accumulator. That is what the instruction. Okay, and LXIH register pair means load the, here also it is same, because the register pair will hold the memory location where your data lies. When you want to load the more than one data, you can make use of this LXI data transfer instruction. Okay, so and the other set of instruction, load instruction, is nothing but LHLD. So here in this case the memory will be directly mentioned in your instruction where your data lies. Here in this, with the help of this instruction, you can load the 16-bit data. Okay, so here in this case 2040, the address is mentioned directly. Okay, so in one 16-bit address, one 8-bit data will be taken. Okay, so whenever the processor execute this instruction, it is taking the data, 16-bit data, from the specified memory location mentioned in the instruction. So here, so I already told you that in one 16-bit data holds a, 16-bit address holds a one 8-bit data. Two 16-bit address holds a two 8-bit data. Here from 2040, one 8-bit data will be accessed and that will be moved to the L register, and next automatically it will be incremented by 1. So when it incremented by 1, so you will have 2041. Okay, and next, so in that memory the higher order 8-bit data will be loaded into the HL register, so that 116-bit data will be accessed from the two successive memory location which is mentioned in the instruction. Okay, so as a summary, with the help of LHLD, 116-bit data can be accessed. Okay, so that is the concept of LHLD. STA is nothing but what LDA does from the memory location to the accumulator, right? So STA, SHLD, all these store instruction and all copy the data from the microprocessor, register of your microprocessor, to the memory location. Okay, so that is the concept of store instruction. So here example STA2500 means 8-bit data which contains by the accumulator will be copied into the address which is nothing but the 2500. Okay, and next STAX means if you have B register means what happens here is the content of the accumulator will be moved to the memory location which is pointed by the BC register pair. Okay, and next SHLD same as like that. So L register, whatever the content which we have in the L register, that will be moved to the address which is mentioned in the instruction. And next, whatever the content we have in a H register, that will be moved to the next successive memory location which is mentioned in the instruction. Okay, so these are the loading and storing operation which is executed by the 8085 microprocessor. So again, you have some set of data transfer instruction, exchange instruction. The content of exchange, in the sense, the content, it can be accessed only with the HL and DE register pair. Okay, so content of a register H or exchange with the content of a register D, and higher order, lower order will be exchanged when you use this instruction. Next, SPHL. So this instruction loads the content of a HL pair into the stack pointer. Okay, whatever the content which we have in the HL, that will be copied into the stack pointer. Okay, and next, XDHL means, so it will only exchange the HL register pair with only with the top of the stack. Okay, so that is what XDHL. And PCHL means the content of a HL register pair is being copied to the program counter. So which means the microprocessor will be loading the next instruction which is pointed by the program counter. Okay, so that is what this. And next, pushing a register pair, in the sense, so the content of a register pair are copied into the stack. For example, if you have push B is nothing but the, I mean, whatever pushing, the operation is moving the data to the memory. Popping is nothing but taking out the data from the memory. So that is what the push and pop operation. During this operation, pop operation, the stack pointer will be incremented because we are popping out, taking out the data. It will be, the stack pointer will be incremented. When you push into it, we are lowering into the stack so that it will be decremented. Okay. So next, when you use external devices, in that case we use some sort of instructions, a specified instruction which is nothing but the in and out instruction. Okay, so out instruction, when it will be used, so whenever you want to send that data out from the microprocessor to the external device, means we use the out instruction. In instruction means whenever you want to get the data from the external device to the microprocessor, means we use a in instruction. So this, the number which is specified next to the mnemonic of the microprocessor is nothing but the port address, the external address. Okay, external device address. Okay, next, coming to the arithmetic and logical instruction, as I already told, that addition operation, subtraction operation. Okay, so addition, add rm. So rm is nothing but r represents the register, m represents the where your data, in memory location where your data lies, is nothing but the add rm. So add b, example can be add b or add m. Okay, so now here add b and m, in the sense, so one of the data we need, whenever you perform arithmetic or logical operation, we need two sets of data. So one of the data which is represented directly here, and one of the data will be in the accumulated defaultly. Okay, so these two data will be added, present in the particular register, mentioned in the register, will be added, and it is stored in the accumulator. Okay, so that is what that will be the function of the register. Add instruction. Add m means a plus m. So one of the data defaultly lies in the accumulator. Okay, so that is what it is. Add register means, so you can see here, add b, we had it in the previous slide. Add b means a plus b, and finally it is stored in a. So here add e, a plus e, finally the data will be stored, and the flag register will be accordingly modified according to the data given. So here, before execution, this sort of data will be there, and after execution, these sort of data will be stored in the respective register, and the flag register will be assigned according to the data processed. So here it is like this. Consider that there is we have a set of data present in the flag register like this, and after the execution, your flag register will be updated, because here you have over bit, so that overflow bit, so that it is 1 over here. Okay, this is what the addition instruction. And addition in the carry in this ADC means addition along with the carry value. So which means here if it is ADCB means A plus B plus carry flag will be added, and finally the result will be stored in the accumulator. Okay, so ADI in the sense whatever the data need to be added will be transparently mentioned in the instruction. So that is what it is. IACI means one of the data will be lie in the accumulator A plus CY plus, which is nothing but the carry, plus immediate value which is mentioned in the instruction. Finally it will be added to the accumulator. Okay, so DAD is nothing but the double addition. So double addition is nothing but the 16-bit content of a register pair are added to the content of the HL register pair. So for example, DADB means BC content of a BC register pair will be added to the HL register pair, and finally it will be stored in the HL register pair. So a corresponding flag will be registered after in a change of the result. Okay, so subtraction is nothing but subtracting the result. 2 minus 1 will be 1. So like that. So R means the register, memory, M means where your data is located, that is pointed by the variable which is nothing but the pointer M. Okay, so example will be sub B. Okay, so in the place of B register you can have any general purpose register. Okay, so general purpose register like C, D, E and H, L. Okay, so like this. So A minus B, and finally the result will be stored in accumulator, and here A minus M, finally value will be stored in the accumulator. Okay, SUI is nothing but the immediate. I represents the immediate. So whatever the immediate data want to be added to the content of the accumulator, that will be mentioned in the instruction. So after subtracting, the final value will be stored in the accumulator. And similarly SBI is represents the borrow value. So borrow value will be subtracted along with the immediate value and the accumulator value. Final value will be stored in the accumulator. Okay, so here again the increment INR means increment the data by 1. So for example, if you have the B content as 2 means, okay, before the execution we are considering B is equal to 2. So this value will be incremented by 2 plus 1. The final value will be 3, and 3 will be updated again in the B register. It is overwritten. So here memory pointer. So whatever the data which is over here, uh, which is pointed by the memory location, that will be incremented by y, and the same data will be stored in the memory location. And similarly INX means it is register per 16-bit data. INX it will be content of the register pair, which is nothing but HL register pair. That will be the content of a register pair will be incremented by 1. If it is a B register in the place of H, the content of a BC register pair will be incremented by 1. And similarly decrement, subtracted by 1. Okay, here also subtracted by 1. So it is nothing but a 16-bit data. Okay, next coming to the logical instruction, we have AND, OR, XOR, NAND, NOR, XOR, like that. Okay, so here the logical operations are similarly. We have rotate instruction, compare instruction, complement instruction. So complementing is nothing but 0 and 0 to 1 and 1 to 0 likewise. Okay, so all that is finally the resultant will be stored in the accumulator. So rotate is nothing but each bit can be shifted left or right. Okay, so either it will be along with the carry, or it will be along with the either with the carry or not with the carry. Okay, and comparative instruction, there are the 3 conditions. Either it can be greater than, or lesser than, or equally. Okay, so all those will be represented with the flag register. Okay, so any 8-bit data. Okay, so complement I told you, right? 0 is replaced by 1 and 1 is replaced by 0. And here you can see here compare. So compare is RM. So here compare R means any registers will be there. So one of the register will be in the accumulator. For example, if you have compare B, B means compare B, CMP B means content of the accumulator is being compared with the B register. Okay, only here the value will not be changed in the particular register. apart from that, your flag register will be changed. Okay, so that is what. So here is the condition. If A is lesser than this register or a memory, whatever it is represented in the destination register, a carry flag will set. If A is equal to register or memory means, or that it is nothing but a destination, zero flag will be set. Okay, greater than means carry flag and zero flag will be reset. So compare operation will exhibits basically a subtraction operation. Okay, so for example, let's take A as a 2 and B as 1. So 2 is greater than 1. So that what happens, a carry flag will be reset. In other case, if you have the accumulator value as 1 and B as 2 means your sign flag will be affected. So in that case, carry flag will be set because we are doing a subtraction 1 minus 2. So we are taking a borrow value. Okay, so that carry flag will be set. And in other case, to check the equality 2 minus 2 means it is 0. So 0 flag will be set. So this is how your compare operation will be executed. And similarly CPI 8-bit data means it is an immediate data. Okay, similarly same thing will be there. The content of the accumulator will be compared with the immediate data which is mentioned directly in the instruction. And similarly analog instruction, and instruction. And instruction is A and A. Similarly A and A, B or A and B. And A, so when both are equal means, 0 with 0 and means it is 0. So when both the inputs are high means your output will be high. Either of the input goes low, your output will be low. So that is the concept of the AND operation. Okay, so this is the mnemonic of it. OR operation. OR operation means OR A B. Okay, so for any arithmetic and logical unit, one of the operands should lie in the accumulator. So this is how it is processed. ORI is nothing but or the immediate value, which is mentioned in the instruction. Okay, next XRA means what happens here, when both the inputs are same, your output will be low. Okay, when both the inputs are different, your output will be high. Okay, that's what the concept of XR operation. Okay, next XRA means immediate data. And RAL. RAL is nothing but rotate accumulator left to 3 carry. Through this operation, what happened? The bit will be starting from D0, D0, D1, D2, D3, D4, D5, D6. Okay, so this is a rotate accumulator left through carry, rotate accumulator right through carry. So here RAR means right through the right mode, it will be shifted by one position through the carry flag along with the carry flag. RAR. RAR and RAR means shifting its bit position one by one through the carry value. Okay. RAL means shifting left bit position by 1 along with the carry value to the left hand side. Okay, so that is what RAN. RLC means left, because it is also a left hand side bit position, moving left shift operation by one position. So what happens here is D7 bit will be placed in the position of D0 as well as in the carry flag. Okay, so here see why we modified according to the D7 bit. Okay, and similarly C is according to the data bit and RRC. Okay, so this is how the concept of the shifting operations which is exist. Okay, and CMA is nothing but complement the accumulator content. I already told you that C 0 to 1 and 1 to 0. Okay, when you use this operation. And next, complementing the carry flag. If you have a carry before an execution as 1 means, when you use, if you use this instruction, after that your carry flag will be 0. Okay, so this is how it will operate. Set the carry flag. So if you have a carry flag 0 means after this execution of the instruction, the carry flag will be 1. Okay, so branching instruction. will disturb the normal flow of the instruction. Here you have jump instruction. Jump instruction, it doesn't have any conduction. It will be directed to this specified instruction instead of normal flow of operation. And JX is nothing but, conditional jumping instruction. Conditional jumping instruction is nothing but, so based on the updation of the flag register, corresponding flag register, your branching will be changed. Okay, so here, which means the program sequence will be changed. Okay, so that is what JZ means. Jump if 0. So these are the set of instruction. Jump if carry, jump if no carry, jump if parity or positive. Okay, so if a sign flag is 0 means it will be directing. Jump if minus means it will be redirecting the flow if the condition satisfied. Jump if 0, jump if non-zero, jump if parity even, jump if parity odd. Okay, so likewise, if the corresponding flag register is reflected according to the certain condition which is indicated over here, and so that your program flow will also changed accordingly. Okay, so, and this is all the unconditional instruction, call instruction. Okay, so whenever this branching instruction is executed, it will redirect the flow of the normal execution, whatever it is mentioned in the instruction. Okay, so once it is done, once it is moved to the corresponding memory location which is mentioned in the instruction. Okay, so when it will return to the main program is that when it is used in the return or some kind of conditional instruction. Okay, so that is what return instruction, that is also, this is also an unconditional instruction. Return instruction also is nothing but redirecting the branch instruction. Okay, so whenever want to move to the main program means this return instruction will be should be used to return back into the main program. Okay, so that is why the purpose of return instruction. And next, control instruction is nothing but no operation. When you want to stop the microprocessor for some moment means you can use the no instruction, no operation perform. Halt instruction, whenever you want to stop the execution means you can, or whenever you have finished the operation means you can use the halt instruction. HLT is the mnemonic. Okay, DA is nothing but the disable the interrupt. So which means in case whenever the external device wants to access by the microprocessor, in that case the external device, whenever the external device wants to be accessed by the microprocessor but the microprocessor is not wishing to accept its request, in that case you can make use of this instruction. Okay, and next, enable the interrupt. So whenever the microprocessor want to access the request of the peripheral device, in that case you can use EI. Okay, so with the help of these instruction you can enable and disable the interrupt. So whenever the external device comes with the highest priority signal, which is nothing but the trap signal, you cannot disable the interrupts. In that case you have the enable interrupt only. Okay, so next, so these are the summary of the data transfer instruction, arithmetic instruction, logical instruction, branch instruction, and all the operations related to the stack, and input and output operations, and machine control instruction. Next, coming to the addressing mode, there are the few sets of addressing mode according to the instruction accessed. So one such addressing mode is nothing but, so before explaining the addressing mode, different types of addressing mode, so we need to know what is mean by addressing mode. So microprocessor has a different ways of specifying the data for the instruction. So way of accessing that data is nothing but the addressing mode. Okay, so here is nothing but there are few sets of addressing mode. One is implied addressing mode, immediate addressing mode, direct addressing mode, and indirect addressing mode. So implied addressing mode in the sense you don't have operand which is mentioned in the instruction. That is nothing but the implied addressing mode. The example of this CMA, HLT, so all this. So when you have a direct control on a units of a microprocessor means in that case you will be calling it as a implied addressing mode. Immediate addressing mode is nothing but if the microprocessor want to access the data directly, in that case the data will be represented directly in the instruction. That is nothing but the immediate addressing mode. Direct addressing mode is nothing but the address will be directly mentioned in the instruction. Indirect addressing mode is nothing but it is represented through the register. The memory location of the data will be directly mentioned in the instruction. So that is nothing but the indirect addressing mode. So you can see over here register, immediate, memory, input and output, which is left out over here. Okay. So here register addressing mode is nothing but, so through the register the data will be mentioned. So that is what these are the example. Register addressing mode. Immediate addressing mode in the sense data will be represented directly, either the memory or the data, whatever it is mentioned directly in the instruction. Okay. And memory addressing, I told you already, direct and indirect. The address will be directly mentioned in the instruction. And indirect means the address will be mentioned indirectly through the pointer, which is nothing but the or through the registers. Okay. And next is input and output addressing mode. In and out to access the external device by the microprocessor. Okay. And next is implied addressing mode. Implied addressing mode, here I told you already that the operand is hidden and the data is to be operated on the available instruction itself. Okay, so these are the examples of it. So this is all about the 8085 microprocessor. So these are all the basics. Okay, so now you'll be able to understand what is microprocessor and what the operations can be executed by the 8085 microprocessor, and how are the ways of accessing the data by the concept of the addressing mode and the applications of 8085 micro practical applications of microprocessor. Okay, so thank you everyone.